Yeah, thank you so much for inviting me. It's an honor and a pleasure to be part of this conference. I really want to start with Gödel's incompleteness theorems, which are in the title of the conference. So from Gödel's theorems, we know that in any reasonable system for the foundations of mathematics, there are statements that can neither be proved nor refuted. And I think it's quite a natural and nice question to ask for examples of such statements. And in particular, we might want to know whether there are examples for unprovable statements that actually occur in mathematics outside of logic. And one important group of such examples is related to Kruskal's tree theorem, which I will recall later. So connections between Kruskal's theorem and logic have been investigated by Dick de Jong and by Diana Schmidt. And then it was Harvey Friedman who showed that Kruskal's theorem leads to really very concrete and very powerful independence results. In particular, Harvey Friedman has introduced a so-called gap condition on embeddings between trees, which makes Kruskal's theorem even stronger. What I want to do in this talk is I want to show you a uniform picture. And it's supposed to be uniform in two ways. So first of all, it's supposed to include various results from combinatorics around Kruskal's theorem. And secondly, it's supposed to explain in a uniform way how these results lead to independence results. Now, these independence results in the region of Kruskal's theorem, they are intimately connected to ordinal analysis. So as far as I know, the only known independence proofs do use ordinal analysis. If anybody knows different proofs, then I would be very interested to hear about them. And yeah, that's my goal, to show how this connection between Kruskal's theorem, combinatorics, and ordinal analysis, how all this fits into a nice uniform picture. I want to start with something very concrete, namely a class of binary trees, or rather the recursive construction of such a class. This class of binary trees I denote by B, and it's characterized as the least collection of objects such that the isomorphism on the slide is available. So let me explain this step by step. First of all, this one here is an order with a single element. The plus refers to the disjoint union, and well, the product is the usual Cartesian product of sets. So what is this isomorphism here? First of all, let me maybe say what the one does. So the one has a single element, which we may denote by 0. And the idea is that the image of 0 under this isomorphism is a tree which consists of a root node only. So let me draw that root as a small circle. And then that second component of the disjoint union allows to generate more trees from that. Namely, so here you have a pair of two trees. So maybe you can also write it as like this. So you have a tree S, and you have another tree T, and you can form the pair of them. And then in order to get a new tree, so this set B is supposed to consist of trees. In order to get a new tree, what you can do is you can add a new root node, and then you can place these given trees S and T above it as its immediate subtrees. And yeah, this new tree with immediate subtrees S and T, I want to denote by this little circle for the root node, and then the pair ST. So to be precise, this B consists of all binary trees where each node that is not a leaf has precisely 2 immediate subtrees, and also you have an order given on the subtrees. You can distinguish left and right subtree. Next, I want to characterize the notion of embedding of trees, and I also want to do that recursively. So the embedding relation on trees that I want to speak about is this inequality indexed by B for the class of binary trees. And before I define this embeddability relation, I want to recall the usual order relation on products of partial orders. Namely, if x and y are partial orders, then a pair xy lies below a pair x prime, y prime, precisely when x lies below x prime and y lies below y prime, so component-wise. And now I want to give a recursive definition of this embeddability relation on trees. And I have two clauses here. The first clause says that S and T, which are the immediate subtrees of this tree here, can both be embedded into it. So the immediate subtree of a tree can be embedded into the tree. And I should probably also say that the idea is that we take the the transitive closure of that relation. So that means if some other tree R embeds into, say, the left subtree S, then this tree R will also embed into the full tree. That's simply from this clause here and recursive closure, and transitive closure, sorry. And then we have a second clause here. And the second clause here says, if you combine it with the definition of the order on pairs, it simply says that if the left subtree S of this tree here can be embedded into the left subtree S prime of this tree here, and the right subtree T of this tree here can be embedded into the right subtree here, then that tree here can be embedded into that tree. So maybe it's also good to draw this, at least on the right side. So you have the tree with immediate subtrees S and T. And then you have the tree with immediate subtrees S prime and T prime. And now if this condition here is satisfied, then what you have is one embedding of S into S prime and one embedding of T into T prime. And then the idea is of the second clause that you simply send the root to the root and keep these embeddings that you already have, and then you get that embedding here on the right side. So this is simply a recursive definition of finite binary trees and of an embeddability relation between these trees. And maybe just to recall this once again, this here with the circle is supposed to denote a tree that has immediate subtrees S and T. If anything is unclear at some point, please do speak up and ask me. So I think there's something is said in the chat. Yeah, there's something in the chat. Are these questions? Does it have the root in the bottom? Okay. Yeah, maybe we can discuss that later. So I now want to show you how this embeddability relation on trees can be linearized in what I claim is a canonical way. Why can't I switch slides? Sorry about that. Okay. So this is about linearizing the embeddability relation on trees now. And the first thing to do is linearizing the order relation on pairs. So in the case of linear rather than partial orders, it's often more convenient to look at strict inequalities. And this, what you have up here, is really the canonical order on pairs of linear orders. Namely, one pair precedes another if either you have a strict inequality in the first components, or the first components are equal, and then you compare the second components. And now I look at the two clauses from before. So this clause here I simply keep. So the immediate subtrees S and T, they are considered as smaller than the tree that has them as subtrees. And then I would like to copy the second clause. So maybe let's just do that. Let's just cross that out for a moment. So then this is really the same clause as before, except that we are now looking at this order relation between pairs in the context of linear orders. So if one pair is smaller than the other, then the resulting trees have the same order. But it turns out that this is no good, because in the linear case, so you could have the case where S is strictly smaller than S prime. So you have this inequality because of the first components, but then you don't even look at the second components in the linear case. So in other words, the second components, they can be completely arbitrary. In particular, it could happen that T prime is bounded by this tree with subtrees S and T. For example, you could have an equality if T prime really can be anything. But then if you use the first clause here and transitivity, then what, sorry, that's not what I wanted to write. It could be that this tree here, no, I think that's what I wanted to write. So it could be that T prime is bounded by the full subtree. No, sorry, what I want to get is that you have this converse inequality here. And how do I get that? Okay. It could be that the T is very large. It could be that this left subtree here, this left tree here, is bounded by the T, because the T can be anything. You've just compared the first component, and the second components can be anything. But then if you're in this situation here, and you have this first rule here, then you get this inequality here. So if you have this inequality, but also that one, then your order won't be antisymmetric. So then you won't get a linear or even partial order. So this is no good. And this is why we need to add this condition here that I have just crossed out. So this is precisely the condition that forbids what I have just done. So in addition to this inequality here, we need to assume as a side condition that both subtrees here on the left are at least bounded by this right tree here. And just to point this out once again, this is not needed in the case of partial orders, because in the case of partial orders, we compare both components. So in the case of partial orders, these components S and T, they will be bounded by one of the components S prime and T prime, and hence also automatically by this tree. But in the case of linear orders, this is no longer the case, and you need to add this side condition. Okay, so even if I got confused in the middle, and I'm sorry about that, I hope to have shown that this really is a systematic and canonical way to linearize this partial order of tree embeddability that we had before. And one nice observation for the proof theorists is that if you now look at this linear order, this really is the addition-free version of the familiar Veblen hierarchy. So it's a well-known ordinal notation system that you get in sort of a systematic way. Okay, so now let me show you two classical results and briefly explain how they are related to what I have said. So the first result is you can linearize this partial order of binary trees with the embeddability relation in different ways. And Dick de Jong has shown that all the linearizations have order type at most epsilon 0. And in fact, there is a linearization of that order type. And you can show that the linearization that I have just tried to reconstruct in a systematic way does have this order type epsilon 0. And then there's a corollary. So Gerhard Gensen has showed that the well-foundedness of this ordinal epsilon 0 cannot be proved in piano arithmetic or in conservative extensions of piano arithmetic. I put that because, well, it depends on the formalization of well-foundedness. Maybe you want to use a second order quantifier. In that case, you should consider a conservative extension. And as a corollary, we learn that this claim here, the collection of binary trees with the embeddability relation, is a well partial order. This cannot be proved in piano arithmetic. Well partial order, for the sake of this talk, let's take as definition every linearization is well founded. I put Friedman style here rather than Friedman because the actual results that Harvey-Friedman proved are much, much stronger and much more subtle, but it's in the same spirit. So this is a concrete independence result from Peano arithmetic. This statement here that the binary trees form a well partial order, that's a restricted version of the Kruskal theorem that I mentioned before. So this is a concrete result from core mathematics that's shown to be independent of Peano arithmetic here. And the connection with what I said before is that we had this systematic linearization here, which did yield the order type that connects with Gensen's result. Okay, so now I want to generalize this example that we have seen so far. And so in the example that I gave, it was crucial that we considered a transformation of orders. Namely, the transformation which took an input order x and gave back the product of x with itself, possibly +1, so plus this single root element added, and then you got the binary trees. And in order to generalize things, we need to look at more general transformations of orders. It turns out that the appropriate transformations of orders are the laters of Jean-Yves Girard. So let me very briefly say what they are. So I want to write LO for the category of linear orders and order embeddings. And a delator is a functor from linear orders to linear orders. So a certain transformation of linear orders that preserves various things. First of all, it should preserve well orders. So whenever you have some well order X, then the image under D should also be a well order. And secondly, it should preserve the categorical notions of direct limit and pullback. Rather than saying what direct limits and pullbacks are, I want to point out one consequence. Namely, 2 and 3 imply that every element sigma of such an order D of X only depends on finitely many elements of X. And these finitely many elements I call the support of sigma. So how does that work? Well, if you have any suborder A of your given order X, and this will be a finite suborder, then you can consider the inclusion of this order A into X. And this inclusion map here, iota, it's an order embedding. Now, because D is a functor, it acts not only on objects, but also on maps. So you get another order embedding D iota, which goes from dA into dx. And now you can ask whether this given element sigma in dx lies in the image or range of this function here. And what 2 preservation of direct limit implies is that for any sigma, there is a finite suborder such that sigma does indeed lie in the range of this function. And preservation of pullbacks 3 implies that there is a smallest such suborder, and this I denote by sub of sigma. So maybe it's good to look at an example. Once again, let D of X be the product of X with itself. So its elements are pairs of elements from X, and the support of such a pair is simply the set of the 2 components. So intuitively, the support is really simply the set of things from X on which such an element depends. Now, once you have this general notion of embedding, you can define a general notion of these linear fixed points that we have seen before. Namely, you can show, even in a rather weak Bayes theory, that when you have any such delator D, any transformation of linear orders, then there is a linear order theta D. So this is the fixed point. So it would be the linearized version of the binary trees that we had before. And the fact that theta D is a fixed point is expressed by the fact that there is such a function theta, which is a bijection, and it goes from D of the fixed point back into the fixed point. And now these clauses 1 and 2, they are exactly what we had in the example, or rather they are a straightforward generalization of this. So whenever something is in the support of a sigma, then this will be bounded by the collapsing value theta of sigma. And this is really just a clause that S and T, the two subtrees, are bounded by the new tree. So this is just a generalization of this clause here. And secondly, we have the other clause from before, which essentially said that this bijection is order preserving. So if sigma is bounded by tau, then theta of sigma should also be bounded by theta of tau. But as before, in the linear case, we cannot have such an order preserving function without side conditions. So we just add the same generalization of the side condition as in 1, namely everything in the support of the smaller element of the sigma should be bounded by the value theta on the larger element. And what you can also show is that, in fact, there is such a fixed point theta of d, which is initial. Initial is a categorical word for minimal, let's say. And it's uniquely characterized by being minimal in this sense. And in the following, I want to reserve theta d for the minimal fixed point, such that there is this function here with these properties. And now what I could show is that, so this theorem in a sense here, it's a limit of certain independence results related to Kruskal's theorem. So various versions of Kruskal's theorem correspond to a specific d, different specific d. And in this theorem, in a sense, you consider all these fixed point for all d at the same time. So the result says that two things are equivalent, once again, over this weak base theory, namely the claim that this minimal fixed point of d is well-founded for any delay to d, and secondly, pi-1-1 comprehension, which is the strongest of the so-called big five systems in reverse mathematics. And I have talked about this result quite a few times, so I don't want to say too much about it now because I want to get to other things as well. But let me very briefly give the proof idea. The idea is once again to use ordinal analysis, and more specifically to use Gerhard Jäger's ordinal analysis of Kripke-Platek set theory. And the point is, or the new thing here, is that you need to transfer this ordinal analysis to beta logic. So beta models are well-founded models. And these are quite important in the context of set theory, also of second-order arithmetic. And what Jean-Yves Girard has shown is that there is a syntactic notion of proof which corresponds to these beta models. And these proofs are called beta proofs. And now if you carry out, or if you transfer Gerhard Jäger's ordinal analysis to these beta proofs that work for well-founded models, then you can show this theorem here. Now, let's switch back to the partial framework. So in the partial case, I have studied this together with Michael Rathjen and Andreas Weiermann. And what we did, the first thing we did is that we extended this notion of delator due to Jean-Yves Girard from linear orders to partial orders. So PO delators are simply certain functors from partial orders to partial orders. There are certain details that you need to care about, but I don't want to give them here. And then just as in the linear case, and as a generalization of the example that we saw in the beginning, if such a transformation W of partial orders satisfies some minimal conditions, then you can construct a least fixed point as well. And this least fixed point I want to denote by TW. The fact that it is a least fixed point, or it is a fixed point, is characterized by the fact that there is such a map kappa, which goes from W of the fixed point back into the fixed point. And then we have the same clauses as before in the partial case, which define the embeddability relation on trees. Namely, if you have some element of the support of a sigma, then this element will be bounded by kappa of sigma. that really just corresponds to, in the example, to the fact that an immediate subtree of a tree can be embedded into that tree. And then also, just as before, this bijection kappa is order preserving. And once again, we don't have the side condition in the partial case. So we have it in the linear case, but in the case of partial orders, it's somehow included in this transformation of partial orders anyway. So I think that that's quite nice that this side condition drops away also in general in the case of partial orders. And what may help is to think of this fixed point T of W as a recursive data type. So we have already seen that trees, or at least binary trees, are one example of such a fixed point, and other recursive data types such as lists or label trees can be written in this form for suitable transformation W as well. And now this proposition here gives a general connection of the linear and of the partial case. So the situation here is you have a transformation D of linear orders, and you have a transformation W of partial orders. So whenever X is a linear order, you will get one linear order here and one partial order here. And the assumption in this proposition is that for any linear order X, this linear order D of X will be a linearization of this partial order W of X. And having this linearization corresponds to having such a map here, which is order reflecting and surjective. And since we are in a categorical context now, I want that these order reflecting maps are natural in the sense of category theory. So you get certain commutative diagrams. And if that's the case, so if you have these natural linearizations, then you can prove in general that this linear fixed point here is a linearization of the corresponding partial fixed point. And this really is a general form of what we had in the example. So in the example, I gave the partial order of embeddability on binary trees, and then I showed this linearization, and that's really just a general form of this. The main application of this proposition will be on the next slide, but I want to point out one nice side effect here, namely this proposition unifies one step in the proofs of several known independence results. So for example, it tells you immediately without any further verifications being necessary that this addition free Veblen function that we saw in the beginning linearizes the collection of binary trees. So it gives you, in a sense, canonical linearizations of partial orders on recursive data types. And I wrote that this is the easy step in several independence results, because in order to show that some statement is independent of a theory, you will still need to do the ordinal analysis of the theory, and you need to understand the linear order that you got in this automatic way. So it doesn't give you a completely uniform proof that simply drops out all the different independence results, but I think it's a very nice uniform explanation of one aspect of these different independence results. Now I want to show you the main result about these recursive data types here. This is another equivalence. Once again, it's one of the equivalent statements is pi-1-1 comprehension, this strong principle from reverse mathematics. And the second statement is a generalization of Kruskal theorem to arbitrary recursive data types. So the original Kruskal theorem was for trees, and here we extend it to arbitrary recursive data types. What that means specifically, what this theorem says specifically is if you are given a transformation W of partial orders that preserves well partial orders, then this fixed point T of W, this recursive data type, will still be a well partial order. What we know from work of Alberto Marcone is that pi-1-1 comprehension is equivalent to the so-called minimal bad sequence lemma of Nash-Williams. And I think that this makes this result particularly interesting because the minimal bad sequence lemma gives an extremely elegant proof of Kruskal's theorem. But in the case of the usual Kruskal's theorem for trees, this elegant proof is not the most elementary proof. So the minimal bad sequence lemma, in a sense, is much too strong to prove the usual Kruskal theorem for trees. But what our result here shows is that this is really only because in Kruskal's theorem we have restricted to this specific case of trees. Once we make things uniform and extend Kruskal's theorem to arbitrary recursive data types, then this very elegant proof via the minimal bad sequence lemma will also be the most elementary proof, in the sense that we have an equivalence between the result and the lemma that is being used in the proof. Okay, so I have started a bit late, so I hope that I still have 10 minutes or so. In the final part, I want to show how all this connects to the so-called gap condition due to Harvey-Friedman. So yeah, let's start with some notation. I want to write Sn of x for the collection of finite sequences which have natural numbers below n as entries, except that the last entry of each sequence comes from some given order x. So this last entry is just some sort of relativization that will become important. But really, it's mostly it's sequences with natural numbers below n as entries. And I want to order these sequences of natural numbers by the strong gap condition due to Harvey-Friedman. And this gap condition here is maybe best explained by looking at an example. So here we have, maybe I should also say, so this gap condition, it exists for embeddings of trees, but you can also formulate it on the level of sequences. In a sense, sequences are unary trees, and I want to look at sequences here simply because it makes things easier. So here you have an embedding between sequences that respects this gap condition. It's an embedding of sequences because this left sequence here can be found as a subsequence of the right sequence via the numbers that are marked red. And for this last entry x, it doesn't have to occur on the right. It's enough if it's bounded by the corresponding entry on the right. And what the gap condition says is that every black number, so every number in the gap between two red numbers, is at least as big as the next red number. So for example, this 3 and the 7, they are at least as big as the 2 that follows them, if there is a next red number. So in the case of this 1 here, there's no condition because it's not followed by any red number. Maybe it's also good to point out what happens if I color this 7 here red instead of the previous 7. Then I would still get the left sequence as a subsequence, but the gap condition would now be violated because this 3 is not bigger than the 7. So I cannot color this 7 here red. Okay, so that's the gap condition. And now my goal is to show how this gap condition connects to these fixed points that we have seen before, to these general recursive data types. Okay, so this is maybe a bit technical, but let me briefly go over it anyway. This is, in a sense, the crucial observation of the whole construction. So this here is an auxiliary order with this top index 0. And this corresponds of all sequences of natural numbers below n+1 in this case, which start with a 0. So that's why you have this top index 0. It's all the same sequences of natural numbers as below, but now you demand that the first entry is a 0, except when the sequence has length 1, because then the first entry will be the last entry, and the last entry is simply an element of your given order, and you also want to include these here. But in general, this consists of sequences with first entry 0. And now I claim that we have an order-preserving bijection between these orders here. So maybe to make this understandable, the whole point is to characterize this order here as a fixed point. And it's a fixed point because you have this transformation from some order with this as argument into this order here. So that's why it's a fixed point. So how does the bijection look like? So let's look at this here, which is an element of that right part of the disjoint sum. So this is a sequence with entries below n. So here are some natural numbers below n. And then the last entry, which is this here, comes from that order. So it's a sequence of natural numbers below n plus 1. And the first entry, J1, if it exists, i.e. if L is not 0, then it has to be 0. And this is mapped to an element of this set of sequences here. This has to start with a 0, so we simply add a 0 in the beginning. Then all these entries are increased by 1. And then this here, this last entry is unraveled in a sense. So you append these numbers, J1 to JL, and then the last entry of that sequence will simply be that X. So maybe two things about this. First, why is it a bijection? It's a bijection because this J1 has to be 0 by definition. And so this J1 is uniquely characterized as the first entry 0 on the right, except for the leading 0. So that's why it's a bijection. And secondly, about the gap condition. So in this example here, I said there was no gap condition on 1, because 1 is not followed by any red number. And similarly, there is no gap condition on this IK, because IK is not followed by anything, only by this last entry from the given order. So on the left, there's no gap condition on IK. In contrast, on the right, there could be a gap condition on IK plus 1, because here IK plus 1 is followed by some numbers and some of them might be red. But the point is that J1 is 0, and the gap condition says that this has to be at least as big as the next number, the next red number. But if the next red number is 0, then the gap condition is just trivial at that point, because everything is at least as big as 0. So on the left, you have no gap condition by definition. On the right, you have one, but it's trivial in that instance because you demanded that there's at least the leading 0 in the sequences in that order. Okay, and then just very briefly, so here we have characterized these sequences with leading entry 0 as a fixed point, but in the end, we might not be interested in the sequences with leading entry 0 only, but maybe in all sequences. And to get them back, we use this isomorphism here. So if we have the sequences with leading entry 0, and then this previous construct n, then we can get the next n plus 1 without that restriction on the first entry by some other isomorphism. Okay, now how do we recover this in general form? And I will aim to conclude quickly now. I just have this and one more slide. So previously we have looked at a transformation of partial orders. And for such a transformation, we have constructed a single order TW as a fixed point. And it's a fixed point because it comes with this bijection. And now we relativize this construction to a given order X to construct bijections like this here. So TW of X is the least fixed point built over elements of X as Ur elements. And that means that we get a bijection from these Ur elements from X, disjoint union with W of the fixed point into the fixed point. Maybe it's also good to look at an example here, so to see that this is not something completely unnatural. So if W of set is the product of set with itself, then the fixed point over X will consist once again of the binary trees, and now it will be binary trees with leaves labeled from that given order X here. So it's really some quite natural order. And the crucial point is that this here, TW, is not a single order anymore now, as before, but it's a transformation of orders, which takes some X as input and gives TW of X as output. And it's not only a transformation of orders, you can also show that it's a functor and indeed one of these delators on partial orders. And now you can use that to reconstruct the gap condition in a recursive way. Namely, define PO delators Sn by the following recursion. S0 is simply the identity transformation of partial orders. Then when Sn is given, you define Sn plus 1, 0 as this relativized fixed point transformation T of Sn. And then to get rid of the 0, you define Sn plus 1 as Sn composed with Sn plus 1, 0. So it's really a rather short construction to describe once you have sort of these abstract building blocks. And now you can show that Sn of 1, so Sn is a transformation, and if you give as input the singleton order 1, then you get something out that's isomorphic to Sn1 in this font, and this is simply the usual set of sequences with entries below n ordered according to Harvey-Friedman's strong gap condition. So by this recursive construction, you really get back the sequences with the usual gap condition. Maybe a few concluding remarks about this. So first of all, how new is it? Well, in the original proof by Harvey-Friedman that Kruskal's theorem is still true with the gap condition. So this original proof goes by induction, and it already contains many of the features that I have used. So in particular, it contains the idea that you have to relativize to a certain input order that is being realized in terms of leaf labels. And also it contains this interplay between sequences with leading entry 0 and without leading entry 0. So these ideas were certainly there. But I think it's very interesting to see that this inductive proof can really be transformed into recursive construction. So originally, the definition of the gap condition was simply given directly on the sets of trees or sequences. And to see that you can really, in a very precise sense, turn this into recursive construction, this is something that I find interesting. I should maybe also say that I'm not the first person to see that there's some recursive construction going on. So there is work of Ryo Hasegawa on this, and also Andreas Weiermann has done a lot on this. And in fact, many of the ideas that went into my work I owe to Andreas Weiermann. What I would describe as my contribution is really this formal framework of delators on partial orders and this detailed proof that you can really very formally write down this recursive construction and get back the original gap condition. Okay, so two more brief things. So first of all, this is the gap condition on sequences. If you want to get the gap condition on trees, you only need to modify the construction a tiny bit. Namely, in this second step here, where you took these relativized fixed points using T, you don't take the relativized fixed point directly, but you compose the previous transformation as n with m, which is the finite multiset functor. And otherwise, you do everything exactly as before, and then you get a strong gap condition on trees. So I think that's also nice that you have this general recursive construction, and if you change it a tiny bit, then you get from sequences to trees. And one second thing, so I really wanted to make the point that there's an extremely close connection between these partial orders and certain ordinal notation systems. And that can also be explained now in that framework. Namely, if you do this exactly same construction, except that instead of partial orders, you work with linear orders, then you get certain iterated collapsing functions that are known in ordinal analysis. Specifically, what you get if you copy this construction here for linear orders, you get the addition-free theta functions as studied by van der Meerenratjen and Weiermann. And in fact, and this is my last sentence, So in this paper by von der Meeren, Ratjen, and Beuermann, they considered two versions of the addition theta functions. And these versions have somewhat different properties. And I can also construct the two versions by simply changing the recursive construction a tiny bit. So it really seems to contain quite a lot of combinatorial principles and things from ordinal analysis in a uniform way. Thank you very much for your attention. And if there are questions or comments, I'm of course very happy to take them.